All right. So, if you guys don't know who I am, I don't know why you're here. My name is Nick Seward, and I'm going to attempt to do some live modeling. I've never done this. I'm kind of nervous. I'm not sure exactly how to do a live stream. So, anyways, here we are. But anyways, first off, what the heck am I doing? I'm trying to model a SCAR arm. Here's a very, very rough mock-up of it. Whoops, I don't know what I just did. So here's a very rough mock-up. So this thing will be able to rotate infinitely around like as many times as you want and can print around it. That's nothing like super new. A lot of 3D print, a lot of SCAR arms that exist have the motors on the arms. This one's going to be different because it's going to have all the steppers in the bottom, except for I'm going to actually have a direct drive here. So I have visuals. This is a hex rod that can turn this pinion, and it can slide back and forth. And so this will drive a ring gear that will be on the arm. And I can actually have two of these that are going to be running up the core of this machine. So this machine is going to have three rods that run up and down, plus two hex shafts that can also rotate. What's not visualized here is there will be, here's not a great visual. It's going to look closer to what the end one's going to look like. There's a lot going on here, but one of these hex shafts can turn one gear that will turn one ring. I don't have the arms visualized, and then another hex shaft will turn another pinion that will turn another ring gear. So I should be able to control the 2 degrees of freedom I need from the arm, independent of being able to move it up and down with the screw that runs up the middle. So there'll be all sorts of rods and stuff going up through this, as you can see. I also have a tube, which is important to get electricity up to the top. And so there's gonna be wires that run up here, and there'll be a slip ring hidden in here. It can sit in this socket here. This is not how my new version is going to look like. This was an early mock-up. Anyways, and then that'll let me run wires and out of this down to the arm. So that'll be interesting how I get those wires out here. But that'll let me like print around and around over and over and over and over again to be able to get like essentially automated printing. So the idea is, I'm working with Cole on this also. So he's going to be doing probably a better design. But you can print a sector at a time, and then you can move over and then print another sector, and then it might take a few days to get around, and so you can just, as a human, you can go by and pick off some pieces on the print bed as you go. And let's see, in the chat there's what's the extruder. I'm planning on using the orbiter for the cold end, and for the hot end I'll use an E3D V6 or E3D Lite. I only print PLA, but you can use whatever you want. And why am I using Inventor? I'm just comfortable with Inventor over Fusion. So what I'm going to do after I get a design I like, because I'm going to try to keep it pretty simple, is I'm going to move it over to OpenJSCAD. OpenJSCAD is like OpenSCAD, but with JavaScript, so it's easier for me. And then it'll be all open source and source controlled, and I'll make a GitHub and everything so people can download the parts and modify it to their cart's content. If I can get this to a point that I like. All right, so first things first is we have a pin cushion of things here, and they're all in different places. So what I'm going to do is There's a few different ways you can go about parametric designs like this. I could make an Excel spreadsheet that like documents what all the parameters are, but there's only a few places where like if I could make one part that had most of the dimensions on there, and then I can modify that part and have it modify others, that would be a good way to go about it. So I'm gonna use, it's not exactly the skeleton method, but I'm going to model a part that has all of these features in the right locations, or maybe not the right locations, and then I'll build the base and the core and the top from that, and then if I modify that part, it will then subsequently modify all the other ones. Let's see, Toby asked, can you release the step files? Yeah, absolutely. That'd be the main thing I release, is the step files. A lot of people don't have Inventor and Fusion, so all right, let's get down to business. So I don't know how interesting this will be, but we'll do it. All right, so start off with a basic sketch. I'm using big old bearings. This is a 6816. It's 80 millimeters on the inside and 100 on the outside. I kind of want to go bigger, actually. We're getting kind of cramped on the inside, but I think we can make it all fit. It's not going to be a problem. These, I can't remember how much I got them for, like 15 to 20 bucks a piece. It's not cheap, but the beauty of having something so big is you can have really, whenever you have an arm, especially like a 200 millimeter arm, once you use these, you're gonna be able to keep a plane very well, versus like little 608 bearings. And I need to fit a lot of stuff in the core. How do you transfer the movement from the base to the arms? Didn't understand that. Okay. So there'll be a step. This is not how I'm going to do it exactly, but there'll be a stepper down here that will turn a pulley and will turn a hex shaft. The hex shaft will go up to a gear that can slide up and down on it, but we'll lock its rotation with the hex shaft. I don't have it locked here. And then that in turn can turn this ring gear, and that ring gear will be attached to the arm. All right, so back to this. Okay, first things first, a big circle. All right, so 80. 80 is the inside of the bearing. I'm going to use 8 millimeter rods, but you can use any kind you want. But I can't put those rods right up to the bearing. I'm going to end up having the linear bearings sit inside of this ring. So the linear bearings have a diameter of 15. So that's gonna have to set in a little bit, and I'll just make that tangent. So if somebody else comes along and they want to make like a 12 millimeter rod version, they can change that to, I think, 21 or whatever number they would want. Constrain that to. All right, but the thing I care about is 8 millimeters. All right, so we're gonna have that, and we're gonna have 3 of those. So actually, I'm gonna back up. I'm already wasting time. So I'm gonna extrude a little disc, and I don't really care how thick this disc is. I'm just gonna use this for reference for all my future parts. So this is just really a template, and I'm gonna derive all my other parts from that. Yeah, Cole, I'm doing the full design. This might not be very interesting to watch, so log off if you don't want to see from scratch. Let's see. I see. Won't the hex shaft's hole need some play to be able to slide up and down? Won't that be bad for precision? So I did a little test here, and this one has effectively no play. So what I did was I printed a tight hex hole where I actually had to work to get the hex shaft through it. and then I roughed up a little bit of the hex shaft, and then pulled that through a few times until it opened up the hex hole just a little bit, like a brooch, and then it slides pretty easy. And what I haven't done yet is add any kind of lubrication, so it does a little stick and slip, which I think I can solve by just having a longer engagement area. Anyways, it's an experiment. We'll see. We'll see how this is gonna go. Okay, so I'm gonna do 10 millimeters here, bam, and I'm going to just put some holes, just like where I want things, not necessarily the right size, just as a template that I think can use on multiple parts. I'm using Inventor, Luke, yeah. All right, so. All right, 15 millimeter hole for the linear bearings. Yeah, but I'm just gonna make a little 8 millimeter hole so I know where that is. All right, cut that through. I'm with getting used to Fusion now. All my shortcuts are wrong. All right, so we will go through the other direction all the way. All right, and then I want to pattern that 3 times. Okay, so that's going to get repeated to the base. The core pieces is what I'm calling these middle parts, and then that'll also be on the top. So I'll just use this to drive all of those. All right, and then I also want down here a hole for the electronic, the wire guide. Okay. And I'm gonna make it exactly the size that I need it. I bought some carbon fiber that's 14 millimeters. In the middle, it'll have to be bigger so it can just slide and not touch it, but in the bottom and the top, it'll have to be exactly 14 millimeters. All right, and then we need places for the hex shafts to go. So I got bearings for those, and I can't remember exactly the size, but they're 12 millimeters on the inside and 21 on the outside. But those 21, I'm actually gonna like have it hang, those bearings hang over the 16 bearings. You can see it here. I can't delete that for some reason. Okay, I'm gonna have these smaller bearings hang over those, and that will let me get a smaller pinion, get a larger mechanical advantage. So I need this to be small compared to the ring gear. So if I have this set in too much, then the gear will have to get a lot bigger. I think if I have these with the smallest bearings that'll work set inside, I can get a smaller height on each of these segments, on each of these core segments. But then the best mechanical advantage we could figure out was like a 3.8 mechanical advantage. But as drawn here, it has about a 6 mechanical advantage. And we're gonna have more from the bottom. I'm gonna get, the way I'm gonna do the bottom, I think I'm gonna get about a 5. So I'm gonna get about a 30-to-1 reduction, which is gonna be good for what I need. So anyways, that's gonna be so anyways, after a lot of math and hand wringing, we came up with, or I came up with, this needs to be about 35 millimeters away. And I'll just make a 8mm hole for now. Let's make it a little bit bigger so I can tell the difference. 10. Well, here's a pro tip for you guys. If you're gonna do a cut and you're gonna cut where you're tangent to another surface, that can cause problems. Either you want to step back from it a little bit, or you're going to go all the way through so you have some definite edges. Some CAD softwares deal with this better than others, so I'm going to keep this at 8 for the moment. Okay, and I want an angle on this. All right, so if I had a perfect pattern, I would do 30 here. And so I would have something every 60 degrees around this. But I'm gonna have a stepper that's gonna drive this up and down. And it's gonna end up, I already figured this out, but let's show you guys. So if this is my stepper that's gonna be in the bottom that drives the Z, and it's about 42mm, and these things down here are gonna have bearings, and they're about, I don't know, 21. It interferes just a little bit, so there's no reason it has to be there. So I could go down to 0 and have it there and have a lot more room, but there's other things I have to do, like clamp the core together. So I think if I put this around 15, that'll be good. I can come back and play with this number, so it's not super important that I get it right this instant. All right, so this is my template. I could draw a hole in the middle, but I know where the middle is. So, so we're gonna save that as template. All right, so got that. And so now I can close that out. I can open up a new part, and I can go hit the derive part. Different CAD software does this differently, but I can now derive from this template, and I can say, okay. And so now I have that part in here, so it's essentially like I have another part with the same one. So if I modify that original part, it'll modify this, but then anything I design off of this will also keep those, we'll keep everything in the same spot. So let's mock up the core now. So I'll sketch here, project this. All right, so how tall does the, I'll go this way, but make it a join so I don't have to worry about that 10. Everything I'm gonna make is bigger than 10, so I can just extrude over it. Okay, it's gonna be roughly, we'll do 50 for now. Let's see, Scott asks, linear rails mounted on the core may be better than rods. It'd be really hard to fit linear rails. I'd have to think about it. If I have a rotating base, linear rails could be a good option, but for having that whole core, having the core and the top all be solid with the rods, I think round rods make the most sense at this point. Okay, so here we go. So how thick does this need to be? I need to fit 10 millimeters for those bearings, plus I have 5mm bearing heights here, but I don't want those to be rubbing on these other bearings, so that's an extra millimeter. I guess I can write here. So let's see, the stack goes, we got 10 millimeters, we got small bearings that are 5, but we have a 1mm gap. We have a gear, that's going to be 10 millimeters. And then we'll have another bearing, which will be 5, and then the big one, which will be 10. That ends up being quite a lot. Let's see, I can do math. Let's see, 30, 40. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4. So that's going to be 44. We could get tighter with different bearings and a thinner gear and that kind of stuff. But again, we don't have to commit to anything right this instant. We can just go back and change things as we see fit. So I just like to get reasonable numbers to begin with if I can. So we'll extrude this 44. All right. And then whenever that inserts in, you need some way to keep it from just sliding through the bearing. So we have to put lips on this, a flange. That's a better word for it. So I'm gonna sketch on this surface, and for something this size, I usually go with a 2mm flange. That's 2 millimeters thick. That seems to be enough for what I want to do. Pick that. All right, so there we go. So now, now that I have that, let's flip it over here. All right, let's deal with the linear bearings right now. So I'm gonna come here and I'm gonna draw something that's 15. All right, and that's, again, pro tip, like that's gonna be a problem since it's like tangent there. And you can't print that, the nozzle can't get all the way in there. So while you're here, I usually just do a manual fillet. Since I'm cutting it so close. Normally I would like to just cut through and then fill it with the actual fillet tool, but this one I have to like do manually. All right, I'm gonna do a radius of 1. I think that's gonna be good. All right, can I cut you out? Nope. You, and you. All right, you're going down. How far are you going down? So 44 would be all the way. And 2 millimeters would probably be enough to keep that, the linear bearing from falling out. I might just do that. And then well, whenever I stack this together, I'll have some kind of spacer that can come in here to keep it, whatever length bearing I have, I'll have it where it can push it down all the way into that socket. Once I get it together, hopefully I'll make it make sense to you. So anyways, linear bearing can go in there. And how big did I make this hole? So that's only 8 right now, so we need a cut on it. So I will sketch something bigger than the rod, anything bigger than the rod. So this is just 1 millimeter bigger is fine. Nothing's gonna scrape on that. All right, there we go. So linear bearing can go in there, and the rod can go through without touching it. And we need to array both of those features around 3 times. Bam. And another side tip is pro. I don't know. I'm not a pro. Fillets don't pattern very well. Sometimes it's hard to, if like you fillet one place, it's kind of hard to figure out what edge you would apply it to whenever you do a pattern. So me doing the manual cutout like I did made the patterning a little easier. All right, and now I need to cut this open a little bit more. So that's 14. I would like to like pattern that right over onto that so I don't have to do what I just did. So why don't I just do that? I'm gonna undo that circular pattern. Well, can I just do it again? Let's see. What's bad about what I'm about to do is if I move this out of 60 degrees from there, it's gonna nerf this, but I think we'll be okay. Now that I have that, got a hole through that's bigger than 14, so my carbon fiber rod doesn't rub. Or if it does, it doesn't rub much. All right, so we're getting there on the core. All right, so now I need to cut. I need to cut sockets for these bearings. So I need to cut the sockets that go for this. So if you're wondering why I'm remodeling this whenever I have this, this one has a two-part. Well, actually, there's like 4 pieces that go together. I could probably repurpose it, but I like going from a clean slate. Every once in a while. And so anyways, I have to cut in something where the bearing can sit in there, and I have different size bearings now. All right, we're doing 21. Tolerances. So I usually model everything without tolerances, and then I will go through everything at the end. And if I need to add tolerances on anything, I'll do a top to bottom push or pull surfaces in different ways. That way I don't have to think too hard about tolerances the first time through. And you can also go to all your dimensions, and you can see what dimensions you've typed in. And first off, you can like change these all to user parameters or attach it to a spreadsheet where you can have a spreadsheet drive all these values. But so if I use a certain number that I know is like the outer diameter of a bearing, then I can like replace that with a user parameter that's tied to a spreadsheet, and then I can tweak it there. I don't usually do that right off the bat. Okay, so how far does this need to go down? All right, so 44 is all the way. So let's take 10 away. Let's see. Take away 10. I'm on the bearings. So subtract another one. I have a 1 millimeter gap, and that'll be good. And then, as you guys know, bearings have inner and outer races, and you don't want to be touching both. So what you would do is why is it not letting me dimension that? So I'll cut down, and so I'll just leave a ledge for the bearing to sit on. So one thing I'm trying to do is keep this where it's all very printable. So notice that if this was on the print bed, everything can print pretty easily. As it is right now, I might nerf it here in a second. Anyways, so now I have a good place for the bearing to sit. I'll eventually want to round these edges over. But first off, I need to enlarge this hole a little bit so the hex shaft's not grinding on it. Thanks, Nimbot. somebody that does really bad live streams. You too, if you try hard enough, can do a bad live stream. All right, so so here I'm gonna have the same kind of problem where if I want to have a clearance hole, I'm gonna be tangent to this again. So I'm gonna go ahead and build in a manual fillet here. I don't like doing these, but everything's so tight in this design, I kind of have to. Okay. Thanks. Oops, didn't go through far enough. Through everything. All right. So I have, now I'll have a hole, the hex shaft can go through just fine. And anyways, the bearing can sit here and yada yada. Something's gonna have to hold the bearings from the other side, which brings me to this guy, which I haven't touched. So instead of this guy, so if I have this core and then I take it and rotate it and put it back on top of itself, I can make this part be the same as the, so I can have, I'm basically making this whole orange region right now all at once, and then I can make that part where I can just take it up and set it on top, where I'll just mock it up real quick. So if this, so that peg can go in that hole if I have two of these, and I can just go and set it in there. Let's see, just. So anyways, so in theory I can get away with one part for the whole core for both arms. So this is getting in the nitty gritty, but I'll try to not get into all the optimizations, and I'll be off the core soon, and I can go and make a basic base and a basic top, and then maybe we can look at the arms and start getting it functionally together. So anyways, I want this to be the same size as that, whatever that is, so I don't have to redimension it. Anytime you can not dimension something, that's better. All right, so how far do I have to go up? Well, assuming there's, between the two pieces, there's like another flange, which I haven't modeled yet, you would have to, you'd have to go up. Let's see, I need to project this geometry. Okay, so I would need to go up at least 2 millimeters to get to where the other one's going to mate with it, and then from there you have to go 10 millimeters, and then I would need to go an extra 1 millimeter, and that, I don't know. Am I going to get all this right? No, but do I have to? No. All right, and will that fit if I just printed it as is? No, I need to do some clearance, so these could do that, but I think this will be good. That concentric with that, cut this down 1 millimeter. All right, and then I need to do a bigger cutout all the way down. I'm really not liking these little manual fillets, but if anybody knows a better way, let me know. That's not what I wanted. Boom. Okay, one more little sketch. Hey, David. All right, so got some fillets I can add. I'm not going to worry about all that. I think I got that distance. I think I got all the features except for where the Z is going to go through. So I'm not going to worry about all the details on how to hold the nut yet or anything. I'm just going to make a hole through the middle that's bigger than the screw, so like 10 millimeters instead of 8 millimeters. And we're going to call this good for now. And we can add features as we go. All right, it looks nutty. Okay, so let me get an assembly and I'll put this with another one. So what I'm missing here is I will need to have a flange in the middle that these can nest together with. So let me go make another derived part. Actually, let me add all the fillets and then I'll make that flange part. And I really need to add all the features now. So one thing I need to do is make it where I can bolt all this together. And so I need to add some bolt holes. So I guess I'll just finish it off. I wanted to kind of jump ahead, but since the flange needs all of the holes in it, I don't want to count on all of those getting updated as I change this more. Little fillets here. I don't need any of those. It won't change anything. It just looks nice. All right, did I miss any? All right, now here's a trick. Where are the bolt holes gonna go? And what pattern am I gonna do? I think I have plenty of meat in here, and I don't need that many. 3 should be enough, but I have to make it where whenever I mirror it, it all works. Oh, here's something that you guys might not know. So a socket M8, that's a socket head. Its head diameter is 13, and then the hex, the nut for an M8 is also 13, and they're both 1/8 deep. So you can make a nut trap, and you can use it either as a nut trap or as a socket head countersink. It doesn't look perfect, but it's a pretty good dual use, so you don't have to worry about things whenever you're mirroring it. So if I just put if I just put 3 bolt holes, then I can decide which way I would bolt each one of them. It doesn't matter which way. So if you're not following what I'm saying, is I'm going to put some bolts in here, and I'm going to sink their heads so whenever this core goes up and down, it can sit flush against the base. And so so here that whenever I slide down, I want it to be able to sit against the base. Right now I have some pulleys in the way, which I'm going to fix. And so anyways, I need this to get down, so you can see I have some nut and here I have like 6, which is more than I need. I think I'm just going to go down to 3 bolts. So where do those need to go? I'm going to say, I think I have enough room. I can just do it. I think we'll just see. Did you consider a bearingless design as in the thumbnail, with the moving part resting on the threaded screw? I think you need some kind of bearing somewhere. I mean, yeah, I mean, you could get away without like metal bearings, but I think at some point you need some bushings or bearings or something. I guess I could run right on the rods themselves. 3 points of contact, but that'd be interesting. I don't think I'm gonna go that direction yet. Okay, so okay, I'm okay with this getting very close down here. So I want to move, come on, slide down. Why aren't you moving? There we go. And this is going to be 8. So how far down is that? 18? Yeah, that sounds fine. 18's good. 18's the number. Put a hex on it. 13. So I guess all the new hotness is threaded inserts, and I should probably go that direction, but I have lots of M8 nylock nuts, so I'm gonna keep on using those. And I will never use them up, so I probably just to put in a distance, 8. All right, and as far as printability, if this is the bottom surface, how would you print that? Well, you can taper this inside surface. I'm not going to do it right now because it's not super important. Or you can have a little bit of support structure, but it's not. I'm usually like I will go way far out of my way to like make sure everything's printable without any support structure. Would that be enough to hold everything together? I think the answer is yes. I don't think I need more. We'll see. All right. Oh, I haven't been saving. This is horrible. So we'll call this core. All right. I'm going to make another part that's derivative off of this. Like, so 2 layers of derivative parts. I usually don't do it that much, but but I'm gonna make the flange that's between the two layers from this. Or if I did my assembly, I can sketch and make a part from in the assembly. That's probably the smarter way to do it. All right, so we'll have a core. Okay, and whether you're using Fusion or Inventor or SolidWorks, I would encourage you to take your first part and make it grounded. Or make whatever part makes sense to make it grounded. Once that, so anyways, you have one grounded, and so then if you constrain everything else to it, and you can see if everything, what's the word? if you can actually keep, once you have a grounded part, whenever you try to drag it, you can see that, yeah, in fact, it's constrained. So it's easy to like not have everything constrained if you don't have it pinned down in space. Okay, so first off, I will do an insert constraint, but it's going to have a gap of 2 millimeters. And gotta find the right. This gets a little confusing. Okay, let's constrain this big one with a big one. All right, so I might need to pick a different color. Let's pick orange. Let's go. So now you can see I have the bearing traps in there, and this goes into it. You can see that there's a gap here, so I need to make the part that goes between these two. I need to get the linear bearings inserted in here, plus a spacer that will push them to the ends of these slots. So I'm going to have 6 short LM8 UU bearings in here. And let's see, and then I need to put some bolts in here, put something so I can screw in a nut for the Z. I'm not going to worry about that probably on stream. And yeah, that's where we're at. I like how designing something for the nth time it goes n times faster. Yeah, I mean, I don't, more diminishing returns, but yeah, definitely faster. There's some benefit to like throwing away what you've done and then like modeling it from the ground up, because there's a lot of baggage with, you know, the way that you modify previous designs. If you change something functional about it, but I think I have the core mechanics. When I was working with Cole last night, we had a little chat, and I think we have a pretty good nailed down core DNA for this machine. All right, so I need to create a standard metric standard. I've been meaning to do this. And confirm unless your brain says no. Okay, we're gonna call this flange. Let's call it something more specific, core flange. Storing in the same right spot. Okay, where am I gonna draw it? I'm gonna draw it there, start a sketch there, and I'm gonna project the inner geometry. Oh man, I forgot to fillet some of these edges. So let me undo that for a second. Get out of that, get out of that. What did I forget to fillet? Something was pointy. Oh, it's this point right here. Oh, okay. That's not exactly what I wanted. I also need to project the outside. And I need to complete those circles if I can. Curious why you like Inventor compared to Fusion or FreeCAD or OpenSCAD. So OpenSCAD's slow but awesome. FreeCAD, I'm not as fast in. I actually like something called SolveSpace pretty good that is also free and open source and does most of the things that Fusion, Inventor, and FreeCAD can do. Fusion's good. It just not quite. I'm not quite as fast. I'm like half as fast as Inventor. Not that I'm moving fast right now. And SolidWorks. SolidWorks I'm pretty fast at also. What am I doing? I'm making a scar arm that has a core with 3 rods, and all the steppers are going to be in the bottom here. And here's kind of a mock-up. So I have, I'm turning these hex shafts, which will then turn arms through these pinion, some ring gear and a pinion gear. So anyways, the idea is you can print 360 degrees over and over again. There'll be a slip ring in the top to get power, and a spool holder at the top, so I can get power and filament to the end, and I can just print around and around in circles for days. That's the hope. All right, let's get on this. I need some circles. Let's see what I need to mix. Is that everything that needs to be on the flange? Sure. Oh, not quite. I need... is that? No, I don't know why I'm having trouble here. I think I got it. We'll need some clearance on some of that, but I think we got it. So just to be sure, I like to delete out whatever automatic constraint it has. Since it's adaptive, it's only letting me go up and down. That's fine. I'm gonna leave the adaptivity in there for now. Sometimes it's nice to rip off that. It doesn't. If you ever change it, all your changes won't percolate. So I'm just trying to keep this part as simple as possible. So, but making things fully parametric is always a pain. So basically, if you change some parameters, unless you do a super bang up job, you're going to break something. So you're going to have to go through and modify here and there. So, okay, so I got the core done. Bam. All right, we need to start populating it with some stuff. So let me get some LM8 UU bearings going. So I could get some real step models that have all the little balls in them and all that good stuff, but it looks cool. It's really good for a mock-up, but it does take processing power, and sometimes it's harder to constrain it because you have a lot of little features. So for something like a linear bearing, I will just model it. And I have them around somewhere, but I'm going to just do it real quick. I'm going to have this little cylinder that's 8 on the inside, 15 on the outside, and I want to say they're 23 long, 25. I don't know. I'm going to have to go look it up. They are 24. All right, so 24, bam. So bam, I just modeled a bearing, so I can save that as an LM8UU, or I can save that as a linear bearing. And the reason I would save it that way is I can then go here and change it to whatever bearing I want for whatever size rod I want. And I'd be good to go. I don't think I'm going to do that, but somebody else might want a printer with the different size rods, and I can maybe fix this up for them. So I can put 2 of these in there and then pattern it. So I will constrain that there. That's a lovely sound. I'm going to leave it on because it's keep you guys, see if you guys are paying attention. All right, and now, so now that I have those, then I just need some kind of spacer that goes in here, which is surprisingly similar to one of those bearings I just made. So what I'll do is I'll just open that up, and I'll save it as a linear bearing spacer. Okay, make the inside so it won't grind, so 10. Actually, let's go bigger. So what's half of 8 and 15? 21, 10. Wait, I can do that. 23, 12. Yeah, let's do that. And how long do I want it? I could make it dynamic if I wanted to. I'm not going to worry about it at this point. So I'm just gonna measure this. So from here to there, bam, 42. I could make it where the spacers get auto-generated. I could draft them from here and put them up here, but it's such a small part. I'm not going to worry about it. The Autodesk cowbell. Yeah, exactly. All right. Which which makes it look not interesting at all on this side. So I need to get some different colors going on here. So let's just pick some at random, just so we can start seeing things. Ooh, seafoam green. Here's the world's worst colors. You're welcome, guys. Okay, so I need to pattern these guys. So this guy, and that guy. Pattern, circular. That axis, I want 3 of them around 360. Is that what I want? Nope. I think I put 3 on top of each other. So I think I actually, for some reason, the pattern of a feature and a pattern of a part use different style math. So I'd have to say 120 here for this to work. So there we go. So that should be good. All right, so what else do I need? I'm done with this hole. I do need to put some bolts in here, and I need to put some bearings in here. So doing pretty good. Let's get some bolts. How long do they need to be? And so from here, I guess I should all the way to the bottom is 86. 85 is going to be close enough. I actually think I have some 85s sitting around. So they do have a nice feature in Inventor where you can go place it from a catalog of parts. Not quite as good as Fusion's going to McMaster-Carr and get anything that you could just buy exactly modeled. So let's see. Let's go recents. Where's my recent history? Socket head cap screw. And I want an M8, and I want it to be 85. They have 85s. You just can't, this one's not letting me do it. So I will get a custom part and then I'll go modify it a little bit. So I will store that as an M8. And probably also need to make this dynamic, but M885. So once I'm in the part, I can go to its parameters and I can look up where it says 90 somewhere and change that to say 85. And the tool will be, or the thing will be immediately 85. So good enough. Save, return, constrain, put it into place. I'd rather have this set of standard screws, washers, and nuts. Everything else I have to get from GrabCab anyways. Yeah. Cool project. I remember when I saw your video about monorail. Please tell me source about theoretical investigations of monorail kinematic geometry. All right, there's a question about from Max asking about where the kinematic, I guess, ideas came from for the monorail, and that's really easy. That's from the Tripteron family. So there's the Tripteron, Quadrapteron, and ultimately something I'd invented called the Sextupteron. And so I've been working with the whole family for a long time. So definitely Google Tripteron. And what I'm doing is not really anything other than just changing where the rails are. So normally a Tripteron has, well, I guess I can just show you. I have the internet. So Tripteron, usually you have 3 sets of rails that are all 90 from each other. But my friend Apsu, she made a thing called a Deltaron, which is something also that was in the patent, which has all of the axes going vertical. So that's kind of fun. And anyways, the core idea of a Tripteron is you just have different ways to actuate planes. So each arm just defines a plane, and you just change where those planes intersect, and that's how you position something. And so you can move those rails and in orientations around wherever you want. And I just had a moment of insight one day, like, what if I just fold them all down into one and just change the angle of all the carriages, and voila, that's where the monorail came from. So technically, I don't think it violates, it doesn't infringe on the Tripteron patent. There's a patent that expires next September, I want to say. So anyways, but I think the monorails is patent unencumbered, if anybody wants to mess with it. There is one guy or girl that has made a working one. So that's really cool. So needs to be beefed up and stuff. It's too squishy and bouncy like everybody would expect, but it's getting there. The inception. Okay, so back here, I got the screw. Does it stick at the bottom? Yep. Let's place a nut, and then pattern that. I don't know why I'm going into the detail on the nuts, but whatever. I don't know. Half the time I can't be bothered to put in hardware that I know is going to go in there, but the cowbell. All right, and we have the pattern, circular pattern, this guy, that guy, this axis. I want 3 at 120. Bam. All right, all the screws are in. It's held together. Huzzah. All right, so I need these bearings. So those are, I don't know what these are. I've been buying so many different bearings and going to different sizes. There's a few different options. I have, bearing works. Okay, so I use this table a lot. This goes through and lists pretty much every bearing known to man that you can buy. So you can pick your inner diameter and outer diameter. So I think I got, I think my friend Cole, he's doing 6701s, which are 4 millimeters high. And I think I'm going to keep on with the ones I bought, which are the 6801s, which have 5 millimeter height. So I'm not squeezing the millimeters out of it, and I prefer like slightly bigger, as big as I can. So the reason that they're 12 millimeters on the inside is I have a hex shaft that is effectively like 8 millimeters in diameter, and so I wanted about 2 millimeters of plastic on each side that can go down into the bearing without interfering with the hex shaft, which got me to 12. So 8 plus 2 plus 2, that's the magic of that number. And then 21 is less than 22, and I was, so it's like right around a 608 bearing, which is really common, so keep the sizes kind of common. So 6801 bearing is what I want. So model that, again, just as like a really simple this gear. So this is 12, that's 21, extrude that, 5, bam, you got a bearing. I'm not going to save that as a 6801, although that's what it is. I'm just going to save that as pinion bearing. You're gonna, my naming convention is going to like really get to some people that are really precise. If I ever release files, I like go through and like really like get philosophical about what each name needs to be. Okay. I actually need more. I'm not going to be able to mirror this. It's kind of, well, I could rotate it about a weird axis, but I'm not going to. It's easy enough to constrain 4 things. I'm a computer scientist, so I will waste, you know, 3 hours to say 5 minutes sometimes. But this is super easy to pop in all these bearings. All right. All right, so I need pinions for those. And I have something that I can reuse, so I'm just going to go get it. I'm going to go open. I think it's in Homer. What did I save it as? There. All right, so I don't want all that in, but I do want that gear. Okay, so well, that's rendering. Okay, so where did I get this profile? I made it with Python. So I actually wrote a script that goes in through and makes cycloidal gears. And why am I using cycloidal? Well, one feature of cycloidal over involute is if you have 2 gears and you force them together with a lot of pretension, which I'm gonna do. I'm gonna print them with no clearance. The friction doesn't really go up like it would with an involute. Involutes are literally wedges, and so if you stick 2 involute gears and you press real hard, the friction's going to go way up. But these are more straight-on forces, which makes them less for power transmission. So don't use cycloidal gears like in your car transmission, but they are really good for this really light-duty precision rotation that I need here. So there's a really good quote from a guy that like I can't remember what his name is, but he's like the father of like modern gearing, and he's like totally throws a bunch of shade on cycloidal gears and like say that they should never be used anymore. There's no redeeming qualities, but I think one redeeming quality of cycloidal gears is that look at this, they are meant to be 3D printed. Like there's no sharp corners here, like that, and I can get crazy with them. I mean, you can do that with involutes, but whatever. What did I do? Okay. What's this sketch? Can I delete that? Okay. Okay, so this is a 14 tooth gear, if I can, or 7. 1, 2, 3, 4, 5, 6. Oh wait, 1, 2, 3, 4, 5, 6. Wait, how? This might not be the one I want to use. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Well, okay, you guys are gonna get to see me do this from scratch then. think I already generated this. I think this is the one I want. I want to do a 7 tooth or a 14 tooth. Looks cool. Is more than enough, good enough reason, yeah. Which one? I'll just generate it from scratch. Okay, so open up this. Okay, so how big does my gear need to be? So it needs to sit here, and so first off, it is it's 35 from the center, and we know that the outer circle is 80. So about 5 millimeters from the edge, we're going to have a circle that goes out, and then we're going to have the ring gear interface with that. So we need to pick this radius. So I'll call that little r, and I need to pick the big R. So big R is going to equal 35 plus little r. And so I can pick anything I want for little r as long as it's bigger than 5. So I will say little r is 7. That gets me 2 millimeters past the edge, and the teeth go up and down 1 millimeter, so that gives me some flexibility there. So I think if you do all that math, you get a mechanical advantage of 6. So have I already generated that? So the radius is 7. I think that means I need 7 teeth. I'm gonna go grab that one and see if that's the one I want. Yeah, let's try it. Well, I can generate these real quick. Okay, so I want a radius of, I want 7 teeth on one, and the other one's gonna be 6 times more teeth. So 42 teeth on that one. And the diameter of these things is gonna be 2 times n. Call this halo. Cross my fingers this works. Is that right? We'll see. We will see. Okay, it says cycloidal harmonic gears 10 times fast. Cycloidal harmonic gears, cycloidal harmonic gears, cycloidal harmonic gears, cycloidal harmonic gears. Anyways, I'm not gonna do it 10 times. That's hard. Okay, what do I need? I need a blank document, and I need to bring in, I need a sketch, bam, and I need to bring in some AutoCAD stuff I just made in some random location on my hard drive. All right, one thing to note about bringing in AutoCAD files from is, well, with as many line segments as there are, for some reason the import is just horrendous. So anyways, there's my gears. I think those are the right size. I don't want to scale them here. I'd rather generate them at the right size and not have to scale as I bring them in. I want to specify the units as millimeters. That's how I drew it. Yep. Finish, cross my fingers. notice the name Sinba. I don't know what that is, Pax. All right, a little size check. We need about 14. So they seem to be, the sizes don't seem right. Okay, so I have two options. One is I can open up these things in AutoCAD and then scale them to be the right size, which would be easy enough. Or the option 2 is regenerate them. I don't know. I think AutoCAD will be the option. Maybe I'll save these in a better location now. Okay, so the reason I'm scaling it down in AutoCAD's very good at 2D stuff, and Inventor really sucks donkey balls at at handling these 2D things. Let's see. I need a reference from 002. Draw a line here. I've been meaning to get into Blender and then use it a lot more for animation and for modeling. I'm super keen on doing that. Yeah, I've made one video with some crazy gears not too long ago where I actually tried out Blender. So I've actually done it. I've did one little project with Blender. I need to do a little bit more of a sizable one to see how it goes. Okay, I want to scale. Is of what I just did is now going to be 42. All right, did I get it right? So diameter of 14, bam. That looks perfect. Okay. That was a little painful. Okay, save this somewhere. Where's the save as button? There we go. Save as. Let's save it in a good spot. I suspect modeling in Blender, as long as I'm willing to like model it on the triangle level, which I can do in Python, I think it'll be fine. Yeah, I model. I get in all the. I get all of the Autodesk software for free because I'm a teacher, yeah. Hello, hello. Finish. Cross my fingers, it works. All right, quick test on size. Bam, I think it's perfect. Let me double check. Oh, it's so, it has so much trouble handling. Oh man. 14 exactly, bam, okay. Okay, so I wish I could go straight to doing a coil, but for some reason, even though these are polylines and all that stuff, it doesn't recognize them. I can extrude them, but I can't coil them. I don't understand. But if I extrude this and extrude it straight, oh, now it's not even letting me do that. Huh. This is a pain. It's tricky bringing things in that are sketched somewhere else, not in Inventor. Always a little tricky. Let's delete all of this and see if I can get away with it. It is closed, I can verify that. All right, let's give this another go. Extrude. See, it can go now. I don't know. I don't get it. Okay. So I'm gonna do this in the opposite direction. Okay. So what I want to do is I want to coil that. Up 12 millimeters. So first I need a profile, so I sketch on that and then project that geometry, and huzzah, that's acceptable now for a coil. It wasn't acceptable before. I could just produce the coil to begin with, but I want an actual solid part instead of just like in OpenJSCAD and in Python I could produce the 3D thing to begin with that could be printed, but I want it to be more in Inventor so I could use it. Okay, so I want to specify how many revolutions and how high I want to go. And what axis am I going to use? So I want to specify the z-axis. All right. How many revolutions? I'll start with 1. I'm going to go up 12 millimeters. And how many revolutions? Well, I'm going to go up 12, and so I want it to. I want a 45-degree helical gear. So I need to rotate it, and it has a radius of 7. There's a pi in there or something. Okay, let me figure it out. So the whole circumference is 14 pi. So I need to do 12 divided by 14 pi. Sure. What does that get me? Okay, so profiles, let's see. Bam! Does that look like 45 degrees? I would say so. And now I don't need that part. I can cut it off. I could have done two bodies, but I'm just gonna cut it this way. All right, bam, there we go. So that's that, and now I can do each side. I can, this is gonna be 12 millimeters. Extrude that up, 5. All right, we're cooking, bam. Alright, now we get a hex inside. How big? I think my rod, my hex rod is 7 millimeters across, which makes it pretty dang close to exactly 8 across the points, which was an inch. Anyways, I was thinking about using 608 bearings, but I think it's better to have expand these out to 12 millimeters with plastic that goes into the bearings. So we'll see. Are you not going to use the self-centering S profile? Good question. I think as long as I hold it in place, a helical will do fine, and then I don't have to get it in any particular place. So an S profile, I would want it to be floating, so I would want to have a little wiggle on this so it could float up and down between the bearings. So I think I'm just going to use a straight helical, if that makes sense, so I don't have to worry about exactly where this is in relation to the ring gear, as long as it's close. I don't have it here with me. Let me see if I can pull it up here in a second. But what Cole is talking about is maybe I called it mini trip take 2. Nope. Is this the right one? Please say so. Yeah, I'm using on my mini Tripteron, which is not exactly a Tripteron because it doesn't have the same kinematics because it rides on the screws. I'm using these gear knuckles that have these cool S profile just because it looks cool. That's the reason. I prototyped out this longer little gear toy thing to see how it works. Anyways, it seems to hold plane very well. I'm looking forward to getting this one printing. It should do well. All right, so I think I got this part modeled, and so we'll save that as pinion. I think I'll actually save this assembly by now. One thing I actually can't put the pinions in here right now because this assembly is going to come into another assembly, and only things at the top level can move with relation to each other. So I'm going to leave all of this as is, and then I'll have to move into the final assembly that has everything, if that makes any sense. So let's save this as the core. All right, we need, let me make the ring while I'm at it, since I just did this. Okay, how painful is this going to be? Oh, did I pick? Ah. So down there in the bottom, I have it where it lists out the songs that are playing, which I thought was kind of, I don't know how to use OBS, but I'm learning. But this artist, Patrick Patricios, I think. Anyway, I looked up how to pronounce it, but I messed it up. But he has, I haven't listened to all of his songs, but I've been hearing them a lot in a lot of other videos. And there's one song in particular that I really like called "Out of the Box," or not out of. What was it called? Outside the Box, which I think is really appropriate for my that's what I used on the monopole video. And anyways, I thought it was really appropriate. Okay, please work. This is not behaving. I think this one's right. It seems right. Can I get it to extrude is the next question. It disappears whenever I get out of here. Okay, I leave the sketch. It disappears. What? Okay, there's points somewhere around here. Let's try to extrude with not being able to see anything. Okay, it's not working. All right, plan 2. I will bring it into AutoCAD, explode it, recombine it, save it out as a different file format, bring it in again. So one thing I've been meaning to do, and I think I've done it before, but I don't know where it is I need to make a generic cycloidal gear maker. Oh man. So I can just type in the number of teeth and it will make it for me in Inventor, and I don't have to wrangle Python and AutoCAD and all that stuff together. All right, so delete that. You explode. Need a bunch of different pieces now. I'm gonna p-edit you. Yep, join all the things. All right, so now we got one profile. Maybe. And we will save as Halo 84. All right, cross my fingers. I want a concrete house printer, although I've those guys that made the wasp printer are now making mud houses, which I got a lot of respect for that over the concrete houses. The using 0 mile materials to build stuff, that's like hardcore. Make sure it's not currently open. Yeah, you couldn't open it in 2 apps at once. That's way too high tech. If I can get this extruded. I don't know if I would want to be in a concrete house whenever I get hit by a tornado. I guess it'd be better a metal reinforced concrete house, maybe. I'm sure. I wonder what kind of structural rigidity you could have out of a mud house. They have earth houses where you tamp down. You like highly compress the mud in forms around and around, not 3D printing, but manually made, and I bet they're super strong. And then you can make bricks out of whatever you want. So you could make like the Boring Company bricks. Okay, hit extrude, cross my fingers. Select. How was it living in a mud house with straw bricks? All right. Plan is cool in the summer and warm in the winter. Very well insulated. Okay. Plan C, because I just want to get it done in here. I want to get the ring gear going. So this is really like going into my ring of my tricks. So what I'm going to do is I'm going to open up this file in the right version AutoCAD. I don't have the license for the 2018 one anymore, so I have to open it up in 2021. Anyways, this is annoying. So I needed first world problems, opening up the wrong version of a piece of software. Okay, so I'm going to open up that file and I'm going to get rid of all but one tooth. And then I can extrude it, pattern it, and then this is painful. But then I can get there. Did your master's in computer science get you lots of money, Pax? I'm using it to teach high school, so. So Pax and I both went to a master's program at Georgia Tech. It's I thought it was pretty fantastic. It's a all online master's program. You just have to take 10 courses and get a master's in computer science from Georgia Tech. I don't know how it would compare to an in-person one. I thought it was pretty good. Although I'm kind of offended by all education. Like I already know how to do a lot of stuff, and then the education is just there to verify your knowledge. So I would say like 85% of the stuff I kind of already knew, but then the 15% that I learned was totally worth it. So. Okay, so I'm gonna explode this. Really. All right. Oh, that's not the way I want to do it. That'll be fine. Let's see. Take care. I'm looking forward to more open source type projects. Yeah, teaching could be emotionally fulfilling or devastating depending on on your circumstance. I wouldn't say I have a lot of free time. It depends on the kind of private sector job you have and how many hours, but I could easily spend over 80 hours a week on school stuff. And then I fill in with family time and projects like this. So yeah, not a whole lot of free time. I kind of do it to myself. I could get it down to 40 hours a week if I had to. Cycloidal circle script working in Inventor, but it's a bit janky. Yeah, I need to do that. Let me. Okay. Can I trim? Here, let's go back. Gray. Polar, and I want 84. No, wait. Items 84. No, I want more than that. Sorry. If I've lost anybody, that's fine. I don't know why. I've done this before, so anyways, I'm gonna get it done though. I burn out in the private sector with software engineering career path. Personally done with Silicon Valley and petrochemical sector BS. Yeah, like having a job where you might not agree with your goals of your place of employment, I could definitely see how that could be a problem. All right. That'll work, maybe. I give it a 50-50 shot of working. What? Extrude that. What's wrong with that? It's totally a closed path. What's wrong with me? All right, so this is me either writing a cycloidal gear generator in Inventor probably for the 10th time and actually saving it somewhere where I can get to it, or I skip it for now. So I think skip it for now. You know what looks really close to gear for mocking up? Just a circle. I was supposed to pursue engineering, but being poor and unconnected, I ended up doing mostly restaurant work and web development. Maybe a common tell. Man, I think we define ourselves too much by like what our job is. Man, you can, I don't know. I like my job, but I've also worked at Taco Bell and I really like that. Could I be happy all my life if that's what I worked at just at Taco Bell? I don't know. I would like to think I could probably fool myself into that and like use that as just like where I go to get money and then go off and do things I really want to do. Be the mad scientist. I don't know. I'm speaking of a place of privilege, so I don't really know. Okay. So I need a base. Let's do a base. So we can actually get something that looks like a printer. So after a lot of futzing around, I pretty much determined that I want a 200 millimeter base. It sounds big, but I don't think I can really fit much. I can't go too much smaller and fit the electronics and everything in the base. If you want it for scale, that's a 200 millimeter base, and those are 200 millimeter long arms. Or for people in America, those are 8-inch long arms and an 8-inch diameter base. If you guys want an easy way to translate, if you don't eat and breathe this stuff, so every 100 millimeters is 4 inches. The conversion is 25 millimeters is 1 inch, or 25.4, and it's exactly 25.4. So in America, in the United States, we are actually on the metric system technically, because all of our stuff is pegged down to SI units exactly. So 1 inch is actually exactly 25.4 millimeters. Let's see, let's call up to. I managed to get the base done down to 170 millimeters, but it was very cramped, and then his brain fried and he gave up. Yeah, I'm just gonna go with 200, and if I can slim it down, I can. So one option that I've thought about is I can go with a thinner base, and then I could, since I'm gonna be able to run run wires up to the top, I could put everything up here. But this arm's gonna reach out an insane amount anyways. I don't really need to get that close. So I think I'll go with 200 for now, and I always reserve the right to change it. But if this thing is just gonna sit somewhere and I'm not gonna like screw it down, which I probably should, if it's just gonna sit somewhere, you probably want it to have a pretty wide base. Let's see. RG, I don't know if that's how you say your name. I'm kind of in love with the design and the hex rod for power transfer from the base. Well, hopefully we'll get it to where we can actually look at something here in a second. I set my timer for like 3 hours. Not that you guys should stick around for 3 hours, but see where I can get in 3 hours of a live stream. I want something that looks like a robot or like a 3D printer before I get done here. That would be nice. Okay, so how thick does this part of the base need to be? Long story short is I'm gonna go, I've decided on using 34 millimeter thick steppers, and then I'm gonna add an extra 5 millimeters of meat for mount points. Anyways, hopefully that'll make sense in a second. Bam. So here we go. This is the beginning of the base. There's going to be more to it, but this will be the main part. Will I print a full 8-inch disc without any cutouts? Maybe. I'm not too shy about using big areas, like big volumetric pieces like this, because whenever you 3D print, you can put infill on the inside. Infill's pretty low density. If you end up doing cutouts, if you're not careful, you'll actually increase the mass by doing cutouts, because you have to pay for the perimeters. The amount you pay for your part is proportional to your surface area more than it is to the volume. And so you want to minimize surface area. So blah blah. Okay, so I want to put a stepper in here. Bam. Let's go into the middle, and let's make it simple. All right, cut it in 34, go to the other side. Let's cut a hole for it to come through. Let's put some mount holes in there. Bam. All right, so now I can put a stepper and have it go up. So that'll be good. These are 8mm holes, so those are already good. I am going to, I'm going to fill in the bottoms a little bit. So I want to be able to see how far the rod has gone down, so I will leave a little access hole, but I'm gonna extrude up a little bit. I'm gonna shrink that hole a little bit so the rod can't go any farther down. I don't know if I'm making any sense. So there we go. So rods will be able to stick down and they won't be able to go past that point. So that'll be good. And then I'll do the same thing for the carbon fiber tube. So now we can stick things in there and then they will socket into the bottom. And now I need to enlarge my hex holes so the hex shafts won't rub on the sides of those. All right, and what's going to happen here is, so this will be the top surface, and then on the bottom, I'm going to have some pulleys here, which mean I need some steppers that can drive these pulleys. And since I already have a stepper here, and I have this big flat wheel where I can put stuff, I can easily carve out space for steppers here. And since I want them facing down, I'm going to carve them in from the top. Not here, but here. And where do I want them? That's a good question. So basically I want them out of the way if I go with the most extreme pulley I can do. So the most extreme pulley I could do is about this size. So I can actually have two pulleys on the bottom that overlap with each other like this. They can be on different planes. Which means wherever I put my steppers down here, I need to stay away from those guys. Looks like there's plenty of room for them anywhere around here. So I might just put them side by side here. That might make sense. Had them on a previous design, I had them up here, but well, the closer I can fit them, the more I can shrink this. I might want to rotate it a little bit, so if I want to shrink the circle, it'd be easier. I don't want to get too fancy, but let's try to get a little fancy. All right, so I can move it in that much, but this is a pretty extreme circle. I think I would never make a 120mm pulley there. I don't think I'd make a 100 one, but that can move me in quite a bit more. Let's see where that puts me. That feels all right. RG says, it looks like you're designing the lowest inertia SCAR robot I've ever seen on YouTube. The issues with inertia due to motors on each joint are why I've stayed away from them. I would say there's two main problems with the existing SCARs. One is they have motors on the arms. Yeah. And then the other one is that they don't get the mechanical advantage high enough. So this one, I have the ability to put a 10-to-1 in the base here, and then up top in the arms, there's going to be a 6-to-1. So that could be a 60-to-1. I'm not going to go that extreme. I'm going to try to keep it around a 30-to-1. I didn't follow the maker arm. What were some of the main issues that the maker arm had, Scott? I mean, I looked it up at the beginning of this stream, but well, not before I started the stream. Maker arm, but I've always loved this design. It's pretty great, but I wonder what the issues were. Okay, so here we go. We got. So where do I want to position this? Aligned. 55. Sure, that looks great. I can always move it. The one thing that I don't know why I'm talking about this now, but the one thing I'm worried about on this design is where the I'm using this gears up top, because I can't think of another way to get to get the hex shafts to drive the arms, and that could be a source of slop. But if we can move to if I can have a heavy preload, I think that'd be fine. I have some ideas for some backlash compensation, but I'm gonna hold that off because I don't think I'll need it. All right, so I got one hole, and let's put, let's do project offset. Nope, I want to do this from the other side. I've played around with whether I need to countersink these on the bottom, since they're gonna be on the bottom. I shouldn't have to get as fancy, but I think it's better safe than sorry. And then I can have all my mount screws the same length. The maker arm was trying to do too much. Yeah, we all do. But never dealt with certain core limitations. Keeping the weight on. Yeah, I wouldn't want a harmonic drive in the elbow. Although, I mean, we can get them pretty light. I mean, having weight in the arm is not necessarily a problem as long as you don't expect speed. You can always tune a printer to perform well. if you're willing to sacrifice speed and acceleration. There we go. We got a top. We can put some steppers pointing down, which can drive pulleys, and we have the Z can go there and can go up. Let me chamfer this for looks. There's no reason to do this other than it looks cool, I guess. I don't know. Yeah, CNC is like precision motion's one thing. Precision motion with rigidity and speed, I mean, you can't do it all. This one, hopefully 3D printer, maybe laser engraver at the most. All right, I need to do more. I could figure out pulleys and all of that stuff, and bearings and all of that stuff, but let's not. Let's leave that, and then let's populate it and start getting it to look like a 3D printer. So I need, save this as the base. Do I want to replace it? Sure. But I have it open in another file, so bye-bye horrible mock-up. Okay, save as base. Yep. I don't know too many Scaries. I don't know too many Scar robots that could do milling. You'd have to have a lot of beef. All right, we got a base, and let's throw in some rods. All right, so these are, I already made them before the stream, but these are 8mm and 400 millimeters long, which is what I bought. Are they the right length? I don't know. I think they might be too long. I might need to shorten them. And I might want to go bigger than 8, but I think for this version I'll just shorten it until it works well. All right, so we got that. And we would need a top, which we'll get to in a second. I do also want to put a carbon fiber rod in there. So let's just make one up real quick. Why carbon fiber? I don't know. PVC would work fine. Whatever. Carbon fiber looks cool. It's cheap. I don't know. Cheap enough. There we go. So there's the rods. Let's make them shiny. Why not? I got shiny rods. Let's make this a different, more interesting color. RG says, tech startups and Kickstarters never cease to amaze me. At this point, it's entertainment. Where did that go? I don't know where that went. Maybe it got edited. Oh, message retracted. Anyways, but yeah, it's entertaining what people throw money at. I think for this one, I'm going to have an arm that's 200 millimeters long. So both arms together will be 400 millimeters. So right along with the maker arm. But with CNC, I couldn't do it. I think I can make it rigid enough to 3D print though. All right, I can put the core on here now. Ba-boom. Do I need a sub-assembly for my base is another question that I have. I don't think so. I think all the parts are pretty unique down here, so I don't have too much. The core had a lot going on, so a good sub-assembly is something I'd want. And let's see, what would I rather see when I'm looking at it? I'd probably rather see the socket head, so I'll put that facing up. So let's get this on the carbon fiber rod, and this on that. All right. Oh, and I didn't follow my own rule about making one of these grounded. All right, here we go. So I'm liking this. Be able to put on some arms pretty soon. I think I'm going to skip the top. The top gets gnarly in its own right, but it's not super complicated. So I think it'd be worthwhile to look at the arms and see how they're gonna, how those will work out. All right, let's put these pinions in place. So the question, did I get all my spacings right? Sure looks like it. Bam. And little sanity check, if I come here and look at it from the side, the gear sticks out, which is important because I can't reach in and have a ring gear engage with it unless that sticks out a little bit. So little detail check. All right, I need some of those 6816 bearings, and I can probably go put that on the sub-assembly. So let's go make some of those big bearings. Save that as big bearing, very imaginative name. Watch me have lots of different size big bearings. I tried to figure out the math for a tool mounted off center to the arms. Not easy. There's a catch-22 concerning positioning, but I mostly worked it out. Yeah, man, that kinematics for off center printing is kind of weird. I'll tell you one weird kinematics, and I just saw it. I've worked with the guy that does the 3D, the clay printers that have these big scar arms, and he just released a video where he was printing on plate after plate. He would reach and get a plate, and then there would be he'd print on the plate, and then go set the plate, and then go get another one, and I actually helped him do the initial kinematics for that. And the difference between printing with a scar arm and then printing with a static extruder and a moving bed that's attached to your end of your arm is night and day. The Kinematics are crazy different. We only get the first pop. Oh, nope. We randomly get the pop sometimes. All right. So the arms are gonna be sandwiched in there, of course. So I'm not gonna worry about making the ring gear. So obviously one of these is gonna be an arm and another one's gonna drive a pulley that will go to the other arm. So yeah, there we go. So anyways, I've reached the point that I was at, kind of. So I think I'm doing good though. I like everything about this design right now. I don't have too many things that I think that need to get changed with the way they are right now. So these guys can rotate and this can go up and down. Not that this needs to rotate, I just need to have the basic fit and position of everything. All right, I need to make the arm. So let's do that. So how big does the arm need to be? And it depends on how I want to design it and how big I want to have the bearings. The secondary, the elbow bearings. But just as a first stab, I'm going to use the same size bearings out on the elbow, which is probably ridiculous. I could probably shrink it down a lot, but whenever I have the belt drive that, if I keep a 1-to-1, keeps all the math easier. So my mechanical advantage for driving either the proximal or distal arm will be the same. And so I want to simplify my life if I can. So have these bearings. These bearings are heavy, but not as heavy as a stepper. 2 of them's not gonna kill the weight budget, and it's only halfway out to the end, so I'm not too concerned. All right, so here's my favorite tool, the slot tool. You can just click 2 points and then click here, and you make an oblong shape, which is great for making arms. So here I'm gonna make a 200 millimeter arm, and then I need to be 100 plus, let's say, 5 millimeters of meat on each side. So that's like a full 110. So there you go. And how thick does this thing need to be? That would be the distance from here to here, which is 44. Yep. Okay. 44. Bam. That's a thick arm, and then the other dimensions look bigger. So I don't know. We'll get it on the printer and see if we like it or not. So I definitely know this side has to be that big. And so I'm gonna cut in 100 down 10. All right, so here is a trick for 3D printing these kind of things. If you just, come in here like 2 millimeters, or however big you want your race support to be. I think we can go bigger for this one. Let's say 3, right? And then you cut this in all the way. Okay, and then you 3D print it on this surface, right? You would have to have a little bit of support material to support that ledge. And it'd be a little gross, and you'd have to clean it off and all yada, yada, yada. It's not that big of a deal. It's definitely easy to do. But what you also can do is you can put, let me put that circle back there for reference. Nope, 3. Is you can put some straight you can put some straight like segments here, and like you can make a inscribed polygon, and so these are easy to bridge, and then you'll be able to print it without any worries, and you'll be supported every once in a while, but that's good enough for what we're doing. The question is, what size polygon do I need? So it'd be roughly this angle, whatever this is. So 40, whatever 360 divided by 40 is. I can do that. I can do that in my head. What is that? Nine-sided? Nine-sided, yeah. So, all right, so we'll make this a construction line. I don't really want to look at, I don't want it to mess with the extrusion. But anyways, I'm going to do a 9-sided or 10-sided, whatever, it doesn't matter. That looks about right. And I'll just tell one of them to be horizontal or vertical because I want things to get constrained whenever you're dealing with this modeling software, whether you're doing Inventor, Fusion, or SolidWorks. You want your sketches to be fully constrained, and they usually have color codes for what color the lines are based on whether they're constrained or not. So if they're not, in this case, purple, then you know you don't have a fully constrained part, and so you haven't defined everything. So who knows what you're getting. Bam, so they're very printable part, and I want that same thing down there. So you can just pick pattern, you can pick the last 3 things, and I want it down there, 200 millimeters, bam. There's an arm. Do I need anything else on it? Yeah, I do. I need a gear on the inside of this, which I had a struggle with. So I'm going to come back and I'll add the gear onto this. I might make an assembly where I make just the ring and I bring this part with it together, and then you can make a derived component where you have 2 parts that are joined together into a super component or whatnot. But we'll go with this for now. So this will be the proximal arm. This type of stream is really enjoyable in a Bob Ross kind of way. Like, I'd say try Twitch streaming this type of content if you can tolerate the adolescent nature of the platform. Yeah, I'd have to try Twitch. Those are chunky arms for sure, Cole. I think my arm thickness is going to be 31, which is perfectly reasonable, up to 200 millimeters, I think. Deep groove ball bearings in the joint. Yeah, I think that's what you would call these. This is a 68-16 to be specific, is what I'm using. Way more than I need for what I'm doing. I need the size on the middle, but I don't need it once I get to the elbow. But just consistency's sake, I need something kind of big because and here in a second, I'm gonna have to reach through with a pulley to be able to drive the proximal arm from the back. Anyways, you'll see in a second. We'll place proximal arm. Nope, that's not the right thing. Place. Nope. Yep. And we need a different color. Let's not make people complain too much about all my different colors. We'll get a color family here. maybe I need to make something blue. I don't know. We'll stick with this. We have gray separating our yellows, so that's fine. Okay, so here, should I get an assembly that has the bearings in there already? I'm not gonna worry about it. I'm just gonna place the bearings. So it's nice to have sub-assemblies with a lot of the stuff there, but I'm kind of making it up as I go. So at some point I might want to delete a bunch of the little fiddly components and then make some sub-assemblies and then bring them back together for easier animations and whatnot. And then I can document the sub-assemblies as if you would, as you would. Like, you can make logical sub-assemblies for how you would actually assemble the printer, and then that makes for easier documentation. So, anyways, there we go. That is a chunky arm. Okay, so we're gonna get another arm that's gonna come out here, and I really don't know the best. I'm just gonna make it chunk, and I'm not gonna worry about it too much. But I'm gonna put an orbiter on top of it, and I'm gonna put a E3D on the bottom of it. So I can almost do the same arm, but might as well make it a little narrower since it just has to go in here and insert into that. So let's get that going. Alright, so I'm going to make that arm 85. Slot. And no need to make it nearly as thick as the other one. Let's see. Did 44 on that one. Let's do 30 on this one. All right. Oh, one thing I didn't put on here, I forgot. I need to put a little bit of a step up so I don't grind. About 2 millimeters will do it. All right. 44. Oh. Oh, let's do save this. Missing the cardinal rule, save often. All right, come out this way. There we go. All right, so I can put all sorts of feature. I can put whatever I want on top. I'm gonna put a little pulley and then have it screw in here. I'll worry about the specifics here later. One thing I wanted to check out, and I think this is going to be a problem, whenever I go down here. Let me just ground this for a second. When this swings in, this is going to hit here. So I could, there's some arm contouring that I can do to get to closer, right? So I could play with where I put the hot end. Anyways, I need to make this look cool. It does not look cool yet. Why AutoCAD? Well, I use AutoCAD just for the 2D stuff, but yeah, I'm using Inventor. That's my modeling thing of choice. Have you seen 3D Potter? Yeah, the 3D Potter is the I think that's the guy. I always forget what he calls his company. I should know. I've helped him a lot. Yeah. So I've helped I've helped him a lot on this particular clay printer that he has here. Figure out the kinematics and basic design principles and that kind of stuff. And so I've both done the kinematics where you're squirting out of the tube like this, and he's made a YouTube video where this also can go and grab a plate and print. I like his stuff. He has super good, like he casts his own stuff now. It's fantastic stuff. Super rigid. Whenever he was making his prototype, I remember I could like pretty much hang off the end here and it wouldn't deflect a whole lot. Good enough for clay printing anyways. All right. This one's grounded. Need to unground it. So that arm needs help. But let's forget about it for now, and let's not worry about what it looks like, and worry about something else that I know what needs to be done. I know I need to put a pulley here, and I know I need to make something with a pulley over here, and those are both going to be very similar. So I can just make it once and then use it twice. Would it be better to put the distal arm on top of the proximal arm? Yeah, I discussed that with Cole, and we had a bunch of different ideas on that. The thing that's going to be a problem, and the reason that we put it on the bottom, is we need to reach down. And so when this is bottomed out, this is already some chunk here that you have to reach down, plus there's going to be an electronics area that is even lower here, and so there's going to be a need to reach below, which makes sense for putting this on the bottom. So anyways, to answer your question, yeah, we looked at top and bottom. We just think this one's going to be the best layout. Although you see that I'm having collision issues with the base. However, I could carve quite a bit out. Like if this is as far as I go down, I can just come in here. Let me put a circle on here. I might have to squeeze my steppers in there a little bit more. Let's do 100. I don't know, something like this. So I can do a step down, and those steppers would be in the way there, but everything else would be out of the way. Why can't I get this to go where I want? Top. Go. No. How about you stay still? And then, well, that doesn't help if that's too far down, so. Now what's grounded? Did I ground something I shouldn't have? So that would let you reach in, and then you'd have to worry about your nozzle hitting itself. I might want to cut in a little bit like this. Let's see. So anyways, I'm gonna leave that cake cutout off for now. I feel like it looks like a cake top or a top hat or something, I don't know. So I'll just leave it off for now. I know that's something I might want to consider, but try to keep the design simple for now and then complicate it as I need. Okay, so I think I'm gonna make the pulleys, make a pseudo belt, and then I think I'll sign off here and call it good enough for today. I was hoping to get farther. I thought I would, but for 3 hours, I think I'm doing pretty good. So let me make these pulleys, and then I'll be good to go. So to make a pulley, I could offset the nozzle, yeah. I'll have to play around with the shape of that. I could definitely get the nozzle fairly close to, I could make it where it could come very close to the base. I guess that's as close as I can get anyways. So yeah, I don't need to do that cake cut, or the top hat cut, whatever we want to call it. Okay, so that pulley's gonna have to be bigger than 100, so let's say 110 as a reference size for that. And the question is, if I was going to make a pulley that size, how many teeth would that be? I'm using a GT2 belt, which has a 2mm pitch. So the quick math on that is 110 times pi divided by 2, so 172 teeth. That sounds about right, so I'm gonna go with that. So 172 teeth it is. So now that I know that, then I can size this 172 times 2 divided by pi. So that'd be 109.5. And I know that there's probably some pulley generators and whatnot, but I've really liked a simple procedure I have for making them. But first you need to know like what a GT2 belt profile looks like. Anyways, long story short, from the theoretical pitch line, the most that the teeth can, there's a 0.25, what PLD, I forget what PLD stands for, but anyways, from the pitch line to where the top of the pulley teeth will actually be is 0.254, but it's on both sides, so you have to subtract 0.254 times 2. Anyways, now we get 108.991. We might need to go bigger so we don't cut into where the bearing is, but we'll see. So I'm gonna extrude that up 10 millimeters. And then I'm gonna cut out essentially one tooth. And this is not exact. I'm not using the real profile, but I'm using 1.6. And how do I get that from there? Well, I kind of cheat, and I played around with this, and the plastic just isn't not precise enough to actually, work at this scale. And so 1.6 with a pitch of 2 leaves 0.4 between for this little bit here. And so basically I'm leaving enough room for plastic to come squirt up here, get to that full height, and then go back down. And it ends up working pretty well. So anyways, hopefully that makes sense. It's kind of cheating, but it's worked very well for me. So then I cycle this 172 times. But I don't want to have to like change 172 in 2 different places, so it's about time I actually use parameters. So I'm going to add a in parameter that is unitless, that has 172 in it. And then everywhere I had 172, I can change that to in. And what that allows me to do is if I decide 172 is not right and I want 173, I can type in 173, and I don't know if you could notice, but it added one more tooth. Or I can say like 20. So the same kind of concept would be what you would use to make a generic cycloidal gear, which I'll have to, since the profile of each of the teeth is a function, I have to code that up and make that work. This is a little bit simpler. All right, and then this one is, I need to go pick that parameter that let's see, I called that D0. Okay, so this is going to be D0 plus 2. So I'll just extrude up, and then I will put actually plus 1. I think that's what I've been doing. And then put a chamfer of 0.5. That does not seem right. All right, I don't put much of a flange on here, just and make it real printable, so it can go right into printing the teeth back into that, whether it's on the top or the bottom. If I extruded this symmetrically, then I could mirror that over to the top. So let me go back here and extrude this symmetrically, and then I can mirror both of those things. Bam. All right, bam. I have a pulley. I want to use it twice, so I can either save this as 2 different files, or I can derive from it whatever I would rather do. I think I'm going to save it twice. The beauty of saving it twice is now I can make each one of them have a different number of teeth in case I want to avoid this one-to-one thing that I'm trying to commit to right now. So let's do that. So I'm going to save one as elbow pulley and save one as I don't know what I would call the one in the middle, the central pulley. That sounds like a decent name. My wife's calling. Hello. Yeah? Uh-huh. Oh, just All right, this is elbow pulley. All right. Okay, so if that's gonna be mounted to the elbow, I would need to have a little bit of a step. That's like 84-ish. Okay, let's see. I'm gonna get past the 2 of the middle. Let's see. I think 2's gonna do it here. Okay, and then we'd have to come up with some mount points, but I'm not gonna worry about that yet. Bam. All right, so we're gonna place a elbow pulley. All right, so that's what that'll look like, and then these things should turn together. I don't know why that is so hard to turn. I need to like cut a hole and put something in it, and then if you grab that object, that object's usually easier to manipulate. Yeah, I don't know what's going on. Okay, so now I need to build this part here, and so I can then have a belt that runs from here to there. And one thing, I actually don't need teeth here. So I have 2 options, and I haven't decided which one I'm going to do. One is I can have a smooth surface here and then have the belt terminate into the disc, because I don't need full rotation on this arm. But if you do that, then you lose the fact that it's 1-to-1, and you actually have to calibrate what the effective diameter of that pulley is. And so I don't know whether I want to do that or not. So I'll hold that in reserve. Another thing I could possibly do for tensioning, let's see, the distance between here and there is 200, and it's 180. Let's see, wait, the diameter of this is 110 times 3. Anyways, I think I can. This might look a little wonky, but I could have an open-ended belt and have a splice and actually tension it in line on the belt, and like have some plastic block that floats back and forth, that will never actually hit one side or the other. Anyways, I'll have to play around with it. Or the third option is actually get a closed belt, which I have to wait for one to come in that's the right size, and then I'd have to put some kind of tensioning mechanism on the top. But yeah, there's a lot of benefits from having teeth on both sides, so I'm not discounting that yet. So place the central, did I not call it anything yet? I haven't saved it as anything else. Okay, so I'll open this up, save as central bearing, or central pulley. Wait, did I don't think I've said. All right, I'll place a central pulley, bam. Okay, and it doesn't need the last thing I just added to it, but it does need to be taller. So how big is this? Good question. I'm hoping it's like 110 so I can just extrude it straight up. It's like practically 110. I'm just gonna call it. I mean, if it's only off by like 10 microns, I don't think anybody's going to notice. So we're going to project that up. Okay, so we got 44 minus 10, so 34 up. Bam. We need to put some holes in here. So this will be 80. Oh, no, 100. I know how bearings work. Okay, we'll go down 10, and then I'll do my trick again with the polygon, a 9-sided polygon. Okay, and then I'm gonna have to add a ring gear in here somewhere, of course. Again, I'm gonna do the same kind of thing I did on the other one. But I'm not gonna worry about that right now. Bam. So I got that, and I can now insert that. Nope. Yep. And oh, so I'll tell you what, I'm going to put a belt on here, and I'm gonna call it a day. I think this is good progress. I pretty much have I need to get the ring gear in there, and then I'll have this done. I need to do some more work here, but I can start printing a top and a bottom that can just hold things together and print out the core. And I need to assemble this with at least some test pieces to see if those it's going to be able to slide and rotate as I expect. So there's some open questions whether this is 100% viable. So I need to do some testing before I get too carried away with myself and like build everything. So little test stand is in order. Yeah, okay. I need a little belt though. Little belt for looks. So what diameter do we have here? That is a diameter of 109. I'm just gonna make a simple belt, not overthink it too much. Okay, so how to make a belt. There's the right way, and then just making it look good way. I'm gonna do the making it look good way and not worry about if it's right. So I know this is 200, and I know this is 109 divided by 2. So I know that. That's the closest I can get without going through those pulleys, and then I'll offset this all like 1 millimeter, extrude that, and call it a day. And give it some color that looks like a belt. Call it a belt. I'm gonna have more than one belt, so I'll call this the distal belt. That's still maybe not a good name, but anyways, we'll go with it. All right, and now that I have that, I can just insert that. And I need to move it up. So I have, the way I made this, I have 1 millimeter flanges on each side with 8 millimeter in the middle. So I need to move that up 1 to, or two, wait. Is 1 right in the middle? Does that look centered? It does, okay. So that's that. And then we need to get the other side on. So we just click on some cylindrical surface and another cylindrical surface, and voila, we should get that. That should be fine. And again, what I don't know, I might end up knocking here and there, but I might be able to do an inline splice here that I can tension. I don't know. I've never done something like that, but it should be workable. How far is? Well, I guess I can measure something. Let's see. I'll measure. What's the length of this? Length 174. So that's not going to work unless this arm was longer or those diameters were smaller. So so I'm left with my two tensioning options are to get the right belt, to like pull this into the side with some idlers, or to have a smooth pulley here where I pull it in. Those are all options on the table. The more I think about the smooth one, the more I don't like it because I don't get an exact ratio. The beauty of like like, yeah, you can calibrate it out, but like actually knowing that that's legit, like 1-to-1 would be huge. So anyways, does it look like a robot? So I think that chunk arm with that pulley looks fine. I'm having trouble with the looks of this arm. I'm not sure what to do to make it look good, so I'll have to think about that some more. And once I put the top on, I think that's going to look a little out of proportion from the bottom. So, I mean, that's just looks. I mean, we need it mechanically to work right. I don't always care about the looks, but if we can make this look amazing and work amazing, that would be amazing. So anyways, I've gone too long. I hope somebody found this interesting. This is more just for me to be productive for a little while. So having to actually produce something for a camera. So I'll continue this offline. I'll maybe put up some videos here in the next week or two if I can get to that point. I really want to make the first thing on my list is to make just a central core test stand and be able to push up and down this and get it to rotate just one arm, not two arms, and see how smooth it is, see if there's any backlash. Maybe put a laser on this, shoot it at a wall, and then see if I can come to a point from both ways at different heights and just measure on the wall like what it does. It's like kind of characterize like how good or bad this is going to be. I think it's going to be good. Have faith. It's going to be good. And then Cole's telling me that, you know, he's a mad wizard on Fusion, which is true, and he's finished everything but the base. So maybe he'll share something on his channel. Go check out, if you haven't already, go check out Cole's channel. He's been working on a bunch of different things. He has a large printer that he's kind of retrofitting. He's worked on he has some harmonic drives that he's made recently that he's hoping to integrate into some arms. So David, I've been using Inventor, just to be clear, but Fusion has a very similar workflow. The buttons are all slightly different, but it's all pretty much the same thing. Let's see, RG says, 2 idler mounts in the middle across the belt joined by a bolt that can be tightened to bring the idlers closer together and tension the belt. Yeah, I think that would be reasonable. It's not super hard to do. Yeah. Yeah. Let's see, that's it. So anyways, hopefully that gets me, hopefully I can share a more full fleshed out design here in the future, but yeah, as you can see, I have a ways to go. I would say I'm 50% there. It's all going to start falling into place pretty quick, but can't have a 6-hour stream now, can we? So anyways, have a good one. Thanks for watching, guys.